Hey classes, welcome back. I wanted to do a quick video today on what we did in class today regarding the dice in our notes, just to make sure that we understand why we're doing it. And if you check out behind me, there's a simulation going on of the makings of a bell curve. And if you look at the little balls being dropped through the little pegs right here, this one is a simulation using a computer, but they have the real thing in a couple places. For example, the Exploratorium, locally they have it. I saw the one at the Boston Science Museum that Bill and I visited on one of his videos. And the point is, I like to introduce the bell curves fairly early because we see it continually throughout the year and it relates to so much. Also, I'm using it kind of as a jumping off point about radiation, radioactive decay, which we'll get to in just a second here. But when you see this right here, we did one in class today with dice, rolling two fair dice, as they say in statistics. Across the hall, you're doing a little bit with statistics, and you notice the curve that it's making right here. And you might get one of the slots being a little bit ahead of the others, but the more and the more and the more you do it, the more even it comes out. The other example that we used along those lines had to do with if you were to flip a coin all day, keep track of heads versus tails. You might have a run of heads, you might have a run of tails, but overall at the end of the day, it would basically even out. We're going to talk a little bit about why we're doing that particular thing with statistics and how it relates to radioactivity. And again, radioactivity, another one of those concepts that comes up again and again throughout the year. Excuse me. But I just want to make sure we have a basic understanding. You see it across the hall in social studies when they talk about carbon-14 dating, how old things are based on a radioactive decay of carbon-14 when it changes into nitrogen. And we know just a little bit, we want to know just a little bit about how that works, because so many of the dates, so many of the things we throw out here in class are dependent upon that. So we start with a brain pop on nuclear power. If you look at this right here, this is a chunk of coal from my grandfather's backyard, as a matter of fact, back in West Virginia. Later on this year, we're going to be talking a little bit more in depth about fossil fuels and coal. But this particular piece of coal is still a good example of how we get most of our energy in the world today. If you charge your cell phone, if you're watching this right now, the electricity that runs it often is from coal burning power plants. And when we burn this right here, a fossil fuel, the remains of once living things, we're looking at breaking the carbon bonds, literally just getting heat out of it, getting turbines to turn, getting steam going in turbines to turn and generating electricity. When you look at the energy transfer we've seen in the classes so far, for example, water power, dams in California, you let water flow through. Essentially, you're turning a magnet around some wires or a wire or wires around the magnet, either way. And you're getting electrons to move. That's the very, very, very basics of getting electricity. If you've ever been to Hoover Dam, you've seen those giant generators there in the dam. If you've ever taken the tour, that's essentially how, when we need more energy, we let the more water flow through. Coal, we just talked about, the coal-fired plants. Wind turbines over the East Bay. If you've ever been over the Altamont Pass, you see all the wind turbines there. Again, they're just spinning to make a generator, to make a magnet spin around some wires, and you're making electrons flow when you do that. When you think about nuclear power now and how it relates to that bell curve that we saw a second ago, it's really essentially a big tea kettle. It seems like it's all fancy, like, ooh, nuclear power, that must be very, very complicated. And it is, of course, but really essentially we're taking those atoms that we learned about and we're taking advantage of one thing. Up till now, we've been talking about atoms as being the basic building blocks of the universe, and of course they are. And remember, they are made in stars. Stars take the hydrogen, put together the larger atoms, if you will, and when you're looking at the bigger atoms that get put together, you have every single element that you see in this classroom, every single element you see around you right now, at one point forged, made inside of a star. The thing is, those 92 naturally occurring elements that we learned about, it turns out not every single one of them is permanent. Some of them eventually do what's called a radioactive decay. They literally fall apart and turn into a different element. When this was first proposed, it was thought that elements were absolutely stable and mutable. They didn't change. Really, once the periodic table, we started to fill in the blanks on the table, we thought, well, that's it. We've basically finished chemistry. Turns out there are some elements. We'll talk specifically about uranium in here. We've already talked about carbon-14. But when these elements fall apart, they release energy. When these elements are releasing energy, we can concentrate them, In other words, get a lot of these radioactive elements in the same place at the same time, take that energy, take that heat, and when I mentioned it being like a big tea kettle, really we're just taking that heat to boil water for the most part. And when we boil the water, we get steam, of course. When we get the steam, we get the turbines going. In terms of the bell curve, when we were rolling the dice to demonstrate this, part of the reason was, not just to introduce the bell curve, when the students did this individually at their desks with their partners, they were rolling the dice for about 5 minutes, and they started to make a smoother and smoother curve. I did it at the board as well. I had a statistical hiccup here when I was rolling my dice. I was rolling a couple of dice up here at the front of the room, and I didn't have that many sevens, which is very unusual. But I guarantee you, the more and more I had done this, the smoother and smoother the curve becomes. I can tell the students, hey, I don't know exactly what your page looks like right now, but I'm pretty sure you're developing a curve that looks something like this. This was written on the board when I was talking a little bit about if you've ever heard of grading on a curve. That's where it comes from, the bell curve of grades. Albert Einstein really was bothered by the idea that we couldn't tell if, for example, if we have a whole bunch of radioactive atoms in the same place at the same time. There's a little bit of space here. I've got, a pen that doesn't work. If you have a whole bunch of radioactive atoms at the same place at the same time, so I'll use my dice as an example. I can't tell you for sure, even if I know all the physics, I cannot tell you for sure which particular atom will decay at exactly what time it will decay, but I can tell you with a large group of atoms that a certain number will decay, will fall apart, will radioactively decay, given a certain amount of time. This is called half-life. It's a concept we'll get to a little bit later, but it has to do with statistics. In other words, I can't tell you exactly what's going to happen with an individual atom, but I can tell you what's going to happen with a group of atoms. Same thing here. I can't tell you what's going to happen on an individual dice roll, but over a whole bunch of rolls, I can tell you a pattern that will certainly develop. Just like the coin flip. I can't tell you what a single coin is going to do, but I can certainly tell you over many flips of a fair coin that you will eventually have half being heads and half being tails almost exactly. So with that being said, that's a little bit of why we're learning a little bit of statistics in here, because radioactive decay comes up again and again throughout this class. It's one of the things that keep our planet warm on the inside. We talk about fission and fusion, certainly what powers our sun, and the things that are powering our civilization right now. And then going forward, when we see the bell curve, that comes up again and again throughout this class when we see biology studies regarding populations. So I'll leave it there. Check out the notes online at pacificascience.org and see you back in the classroom.